So, having discussed the practical utility of shocks in astrophysical situations, and remember, shocks are essentially important in astrophysical situations because they serve as sites for particle acceleration, right? What kind of particle acceleration? High energy particles, right? So, the high energy particles are not part of the general background fluid flow, as we have emphasized over and over again. But these high energy particles are the ones which emit photons, often high energy photons, but not necessarily, sometimes optical, sometimes radio photons, which are considerably low energy. But the point is that most often it is not the background fluid that is observable. It is really these high energy accelerated particles that are observable, that are essentially the tracers for the observations that we make of astrophysical sources. And many times we are puzzled as to the origin of these high energy particles. How did these high energy particles come about? So, this is the question one asks quite often, and shocks in astrophysical situations often provide the answer. Okay. They serve as agents to accelerate such high energy particles, and as we discussed the concept of Fermi acceleration using a shock. And just to recap, there are two basic ingredients in this entire mechanism. One is the concept of scattering centers, magnetic scattering centers, which are also not part of the background fluid, but which are embedded in the background fluid, and these scattering centers can be magnetic irregularities or something else, right? And so these high energy particles bounce off of these scattering centers. These scattering centers serve to, in the way we discussed it last time, they serve to reflect these high energy particles, okay? And these scattering centers simply go along with the bulk flow. Whatever the bulk flow does, they also do, okay? And the other important thing is that the name is diffusive shock acceleration, right? So, it is very important for diffusion to happen in the vicinity of the shock, which enables these high energy particles to sample both sides of the shock, both the upstream and downstream side of the shock, and therefore they can undergo approaching collisions on both sides and gain energy very, very fast, okay? And this kind of acceleration is called first order Fermi acceleration. The other thing about diffusive acceleration is that just like they are able to diffuse on both sides of the shock fairly close by, they can also diffuse far away. So, they can escape from the accelerating region. So, both these ingredients are needed, acceleration as well as escape. Okay. So, this was a very quick recap, a quick run through of why and how shocks are important for our purposes in astrophysical situations. Now, we will turn our attention to one such astrophysical situation where shocks are known to form, that of supernova explosions. Okay. And in particular, we will approach supernova explosions from the point of view of spherical blast waves. So, just to emphasize, we are really talking about driving shocks. What kind of shocks? These kind of spherical blast wave sorts of shocks. Okay, so this is the physical situation we are investigating. As we will find out later, it's even more restricted than this, in that we will be investigating only one phase of the evolution of these blast waves, which is the phase where the shock is known to expand self-similarly. So, our analysis is actually quite restricted, but it has the advantage of simplicity, and it has the advantage of predictability, and historically this was one of the first sort of stepping stones in understanding the formation of shocks in astrophysical situations. So it's important for us to go through this, right. So unlike the situations, the lab kinds of situations which we've encountered, where you might have a tube and a piston, right, and the piston, so this would be a tube, and an airtight tube, and this would be a piston, and the piston will be going forward, and when the speed of the piston exceeds the speed of sound, it drives a shock wave in front of it. Okay, so this would be an example of a piston driven shock. Okay, and so this kind of a thing would be important in lab situations, and also in some astrophysical situations, such as the case of a coronal mass ejection from the solar corona. Okay, so the coronal mass ejection is essentially a blob of plasma which is plowing through the heliosphere, and so that blob of plasma plays the role of a piston. Okay, and so that is pushing material, and once it gets supersonic, it drives a shock in front of it. However, the kind of shock we are talking about is not a piston driven shock. Okay, these are not piston driven shocks. These, on the contrary, these are due to a large amount of energy being deposited at a point. Why does this also produce the shock? You remember, a shock is essentially produced due to a pressure pulse. Okay, a pressure pulse, which a pressure pulse like this. This would be X, and this would be P. Right, and the fact that the peak of the pressure pulse has a different sound speed, because the y-axis is so large, the pressure pulse is so large that the peak of the pressure pulse has a different sound speed from the leading edge of the pressure pulse, and therefore the peak tends to overtake the leading edge, and leading to shock formation. So now this kind of pressure pulse can be produced due to a large amount of energy deposition at a point, a localized kind of energy deposition like this, like what we're talking about here. Okay, and this essentially happens during a blast. Okay, so the other assumption is that this entire thing is happening in a uniform unbounded medium. Okay, you deposit a large amount of energy at a point, and the medium itself is uniform and unbounded. There are no boundaries. Okay, so just to simplify things. For instance, a bomb explosion. This is the prototypical example of energy deposition at a point in a uniform unbounded medium, a bomb explosion. And so you can immediately, or a supernova explosion. Okay, turns out that the physics in both these cases is very similar. This problem was investigated independently by Sedov. The early 1946 and 1959, you can see that there's a large gap in between 1946 and 1959. So Sedov in the Soviet Union and Taylor in the US in connection with nuclear bomb explosions. So really, this is what drove much of this kind of research. Okay, research into nuclear bombs. So the people who understood bomb explosions also recognize that supernova explosions would probably involve the same kind of physics. It also, in that, just like a bomb explosion which deposits a large amount of energy at a point or in a very small area which can be idealized as a point. Just like that, a supernova also, when the thermonuclear flash happens at the center of the supernova, it also deposits a large amount of energy in a very limited region, and therefore it can also drive a blast wave, more specifically a spherical kind of a blast wave, in a manner very akin to bomb explosion. So the physics was very similar. And as you can also imagine, a little bit of history about this. As you can imagine, since research on nuclear weapons and everything was a big deal during those days, much of this research was classified, and so it was not published in the open literature, which is why between 1946, which kind of explains this large gap between 1946 and 1959. Okay, although this research was mostly theoretical, nonetheless, the application was to bomb explosions, and therefore it was openly published, at least in the West, only after the end of World War II. And World War II ended around 1945, right? So you can see that the publication took place in 1950. Okay, so this is a little bit of history. Right, coming down to the physics. What are the central characteristics? Well, the amount of energy deposited at a point, I must say, point, or in a very localized region, it's so large that it propagates an outward propagating spherical shock. What it does is it just produces a pressure pulse that's very large, like this. So, or if you wish, let us not call this x, let's call this r in spherical coordinates. And so the pressure pulse produced by the amount of energy deposited is so large that it produces an outward propagating spherical shock. Why? Because the sound speed here, the Cs here, Cs1 say, and if the sound speed here is Cs2, like this, Cs1 is greater, in fact much greater than Cs2. This amplitude is so large that Cs1 is much larger than Cs2, so this guy overtakes at the leading edge, and it leads to a steepening of this front, and it eventually leads to the formation of a shock. Okay, the other principal assumption is that the shock propagates outwards in a self-similar fashion, and this is a very important word. It's important to understand what this means, what self-similarity means. You're already familiar with the concept of self-similarity. In fact, consider two similar triangles, okay? Say two equilateral triangles. One equilateral triangle is small and the other equilateral triangle is large. But they're similar in that the angles are the same. So this is simply a larger copy of this. Okay, so these are similar. In what sense? In that this is simply an enlarged, blown up copy of this. The angles are the same, right? So it's the same concept for self-similar shocks, in that the spatial configuration at a later time appears like, in this case, it is an enlarged version. It can also be a shrunken version, but in this case, since we are considering an outwardly propagating shock, it is really an enlarged version. So it looks like an enlarged version of the configuration at an initial time. So in other words, if the spherical shock front was somewhat like this at an initial time, later on it would appear, suppose this was how it appeared at an initial time, later on it would appear like this. Whatever this is, if we are sketching pressure contours or density contours or so on and so forth. Okay, so this is one of the central assumptions that we will adopt, and there are two reasons for adopting this assumption. Number one, it leads to a drastic simplification in the mathematics. You really do not have to consider partial differential equations, the partial differential equations reduced to ordinary differential equations. So this is one advantage. The other advantage is that it is quite motivated by observations. Observations strongly suggest this kind of self-similarity. Okay, all right. So for the time being, let's proceed ahead and noting that these are the central assumptions. One of the central assumptions is that the amount of energy deposited is so large that it leads to shock formation. It leads to the formation of an outward propagating spherical shock. The other assumption is that the shock propagates outward in a self-similar fashion. And self-similarity is usually a good assumption, at least for the energy conserving adiabatic or what's often called the adiabatic phase of blast wave evolution, and this adiabatic phase is the only phase that we will consider in our analysis. We won't bother about the other snow plowing phase or so on and so forth. Okay, it makes analysis a little restricted, but that's okay. All right, we can at least be complete in our analysis and draw a number of very useful conclusions. Right, so we will study supernova remnants as an illustrative example. Supernovae, to give you some astro background, supernovae are essentially stellar explosions. Okay, and this happens when the core of an aging massive star undergoes gravitational collapse. So you see, a star, the surface of a star is held in equilibrium due to a balance between several forces. You have the core pulling the outer layers of the star inwards, okay, and so that's the gravitational attraction. And then there's energy produced in the core, and that produces photons, and photons have radiation pressure of their own, and they exert outward radiation pressure, and also the overall material is hot, okay, so there is thermal pressure. So the gravitational inward attraction due to the fact that the core is massive, the inward attraction is balanced by the outward action of these pressures, and the star is in equilibrium. Often what happens is during the course of stellar evolution, the core becomes so massive that one force, the gravitational attraction, predominates over the tendency of the pressures to resist this gravitational attraction. And so during such a phase, and this can happen only under certain very specific conditions for certain very specific initial masses of the stars, but it happens quite often. And so what happens is it undergoes gravitational collapse. Okay, so the core cannot resist gravitational collapse, and it collapses. Okay, and in the process of collapse, it releases a burst of gravitational potential energy. Okay, and in what way? For instance, a white dwarf can ignite enough material from a companion to ignite. Can accrete enough material from a companion to ignite runaway carbon fusion at its core. So what happens is once the core collapses beyond a certain critical density, during what's called the main sequence of stellar evolution, like for instance our sun, what's happening in our sun right now is that hydrogen is being fused to produce helium. Okay, but that's because those are the density and temperature at the core of the sun is conducive only for that particular fusion reaction to happen. However, if the density at the core of the sun increase beyond a certain critical threshold, then it could ignite runaway carbon fusion. Okay, so heavier elements will start getting fused. This is never going to happen in our sun, simply because of the initial mass that the sun, the proto-sun, started out with. But in other kinds of compact objects, such as a white dwarf, the density at the core can often become so high that heavier elements such as carbon can start getting fused at its core. Okay, and the density becomes so high because of gravitational collapse. Okay, so this is a sequence of events. the white dwarf starts accreting material, and then the material accumulates at the core, and beyond a point the core becomes so massive that it cannot withstand gravitational collapse. The material collapses, and once the material collapses at the very core, the density becomes so high that it ignites carbon fusion, which is the next sequence. After helium, carbon starts getting fused. Okay, and what's more, the carbon fusion is runaway. It's unstable. Okay, and so it results in a thermonuclear flash, and that is a supernova explosion. So what happens is at the very core, the runaway carbon fusion ignites a thermonuclear flash, and that is essentially the bomb-like explosion that we're talking about. So this results in a thermonuclear flash. This is essentially the explosion we're talking about. Okay, this is the bomb, so to speak. This thermonuclear flash is the bomb. Okay, from now on we will study the evolution of the blast wave driven by this by this quote unquote bomb explosion at the center of a supernova, which happens due to these two reasons. Okay, there are some very interesting things about supernova explosions. They enrich this interstellar medium with heavier elements. Otherwise, you see, the interstellar medium contains mostly just ionized hydrogen, maybe a little bit of helium, but that's about it. No other heavier elements could have existed. Okay, so what happens is, because of the fusion of heavier elements at its core, the heavier elements are cooked in the core. And when the core explodes, these cooked heavier elements are thrown out into the interstellar medium. Okay, so in some sense, all of us, we are made of heavier elements. We are not simply made of hydrogen and helium. We have all kinds of other elements in us, right? And where did it come from? It came from inside of a star. Okay, that's the only way. I mean, the interstellar medium could have gotten quote unquote polluted with heavier elements. There are some other things about, the heaviest beyond a certain element in the periodic table. Even supernova explosions could not have cooked these elements, but that's a slightly different matter. But most heavier elements have been synthesized inside a star, and so in some sense, this is all of us have been inside a star. In some sense, all life. Not just us, but the rocks and the inanimate objects, everything that we see around us. Now, at some point, we were inside a star. That's where we all began. Okay, so this is a bit of a philosophical, detour. Now, the other thing, of course, is that the reason we are discussing this in a fluid dynamics course is that these supernova explosions, they drive shock fronts. Okay, and these shock fronts accelerate cosmic rays. Cosmic rays are simply accelerated also charged particles. And it turns out that these accelerated charged particles permeate us all over. Cosmic rays are ubiquitous. They are everywhere. Okay, as we speak, we are bathed in a shower. The Earth is bathed in a shower of cosmic rays, and cosmic ray detectors on the Earth detect them all the time. There's a constant rain of cosmic rays on us. So it's always been a very interesting question. Where did they come from? How did these particles get accelerated? And we know from what we discussed in a couple of in the preceding couple of sessions that shock waves, shock fronts are ideal candidates for accelerating particles such as cosmic rays. Okay. What's more, the expanding shock front can also trigger new star formation. You see, you have the expanding shock front, and as it propagates through the interstellar medium, it snowplows material in front of it. Okay, so material is piled up in front of it. So in front of the shock, you have excess material. excess density. And this excess density, sometimes the density is so large that you can have smaller episodes of gravitational collapse, and it can lead to star formation. Okay, it can lead to the formation of new stars. For an astronomer, these kinds of reasons these are the kinds of reasons why supernova explosions are useful. Okay, but for us in a fluid dynamics class, we simply want to sort of understand how the evolution of the shock front, and to a slightly lesser degree try to understand how these shock fronts result in particle acceleration. And here are some pretty pictures of this is not all just speculations. This is one particular supernova remnant called Tycho supernova remnant, and this is a multi-wavelength picture of it. Multi-wavelength meaning it's a montage of say X-ray, radio, and optical wavelengths, and each of these wavelengths is assigned a different color. Okay, so these different colors represent different wavelengths, not necessarily visual, not necessarily wavelengths that can be observed by our eyes. Okay, but the one thing to observe here is the incredible spherical symmetry. This is a real image, by the way. Okay, in taken at different wavelengths, and these different wavelengths are superposed with each other, so that you get a panoramic view of this supernova remnant. It's truly astounding, one of the prettiest pictures in all of astrophysics. The thing I wish to draw your attention to is the incredible near spherical symmetry of this entire object. Okay, this is why we are well justified in thinking or talking about a spherically expanding blast wave. Okay, this is the reason. So it's not simply mathematical convenience, as we will discover later. It's also physical evidence such as this. And here is another very nice picture of the same object Tycho supernova remnant, except this is only in radio. Okay, now the color scale is such that red represents highest intensity, yellow represents the next lower level of intensity, and blue and black represent lower intensity. So what this is saying is that at radio wavelengths, this Tycho supernova remnant is brightest at the rims. Okay, and we know that this emission, radio emission, is produced emission is due to accelerated electrons, okay, or non-thermal electrons. And we can clearly see from this image that the radio emission is highly concentrated at the rim. So all over here, these are essentially telltale signatures of accelerated or non-thermal electrons. Okay, and we know what are good agents for accelerating electrons? Shocks. Hence our whole basis for discussing this. This is most likely, this is a very strong piece of evidence to conjecture that this is most likely the spherical front essentially is a spherical shock. Okay, is an expanding spherical shock. Why? Because we are seeing signatures of accelerated electrons observable in the radio only at the spherical front, not at the center. Okay, and therefore this spherical front is most likely an expanding shock. And when we meet next, we will study the time evolution of this shock front. So that is what we will study from now on. So that's all for the time being. Thank you.